Everyone, my name is Siti Shahida Sharipuddin from UiTM Johor Campus Pasir Gudang. I am pleased to present our research entitled An Innovative NSM CFRP and FASMA Strengthening System for Corrosion Damaged RC Beams. This research was carried out by the research team from UiTM under the supervision of IR Dr. Ruqayyah Ismail. Reinforced concrete is the most widely used construction material because of its strength, durability, versatility, and cost-effectiveness. However, corrosion remains the primary cause of deterioration, accounting for 70 to 90% of damage in RC structures. Corrosion reduces the cross-sectional area of reinforcing steel, weakens the bond with surrounding concrete, causes cracking and concrete spawning, and ultimately reduce structural strength, durability, and service life. Existing conventional strengthening techniques also have limitations. Steel plate strengthening is susceptible to premature debonding and corrosion, while reinforced concrete jacketing increases member size, structural weight, and construction time. Therefore, a more efficient strengthening solution is urgently required. This study evaluated two advanced strengthening materials independently. CFRP provides high tensile strength, lightweight, and excellent corrosion resistance. In contrast, FASMA offers recovery stress, self-restoration capability, and improved ductility. The structural performance of these two strengthening techniques is then compared experimentally. What makes FSMA a smart material? After thermal activation, it generates recovery stress that creates internal pre-stressing without hydraulic jacks. This improves beam stiffness, delay crack formation and crack propagation, and extends the service life of RC structures. Thus, this research has three main objectives. First objective is to assess the flexural performance of corrosion damaged RC beams. Second objective to evaluate the effectiveness of NSM CFRP strips and FASMA in strengthening corrosion damaged RC beams. Finally, to compare the effectiveness of both of these materials in improving the load carrying capacity, deflection, and failure behavior of corrosion damaged RC beams. This is the research novelty, including extending infrastructure service life, improving strengthening technology, reducing maintenance costs, and supporting sustainable construction aligned with SDG 9 and 11. Which consists of three main phases. RC beam specimens were prepared by assembling the reinforcement cage, installing it inside mold, and casting concrete according to the design specification. Threaded corrosion was produced using the impressed current technique. The reinforcing steel acts as the anode, a stainless steel plate serves as the cathode, while a 5% sodium chloride solution simulated marine environment. The strengthening procedure began with groove cutting along the beam soffit using near-surface mounted technique. After cleaning the groove, CFRP and FASMA strips were installed and bonded with epoxy grout. Thermal activation was applied to the FASMA strip to generate recovery stress. Time potential measurement confirms successfully corrosion induction. The finding shows corrosion reduced the ultimate load. After strengthening, both NSM CFRP and NSM FASMA restore more than 90% of the original beam, with FASMA achieving highest performance. Corrosion caused a 25.7% reduction in load capacity. NSM CFRP improved the ultimate load by 22.5%, while NSM FASMA achieved an improvement of 24.6%. This innovation has strong commercial potential for strengthening aging structures. It offers lightweight, durable, and sustainable alternative to conventional rehabilitation methods. In conclusion, this innovation demonstrates both NSM CFRP and NSM FASMA strips are effective strengthening techniques for corrosion damaged RC beam. In compared to NSM CFRP, which is traditional method, NSM FASMA provide additional benefit of self-pre-stressing through its shape memory effect. This research was funded by Fundamental Research Grant Scheme FRGS under Ministry of Higher Education. Everyone.